I went over it briefly in the last class, but we're going to go into greater detail now. And hopefully it didn't mess up the order of the slides whenever I uploaded this. Okay. And so the first thing that we need to do is just go over some of the principles, the basics of the electromagnetic radiation. Because remember, this is all the same spectrum, whether we're talking about X-rays to gamma rays, IR, ultraviolet, or visible light. It doesn't matter. Those are all the same spectrum of things. It's just that our eyes only perceive a very small portion of that spectrum. So this should all be a review from Gen Chem. And this is just looking at only the electromagnetic part of the spectrum that we see with the visible light. And so for those who aren't color challenged, you should see different colors there. But this is to review this fact that since the speed of light is a set constant, you are going to have an inverse relationship between the frequency, the nu, and the wavelength, or the lambda. So therefore, the longer the wavelength it is, the lower the energy. And so because we get that from the whole, where we can substitute in, here, since E is equal to H nu, and nu is equal to C over lambda, then you could say this is true. And so therefore, that's why for us to have a large E, or high energy, you have to have a smaller number here on the bottom. And so this is just the order of the order that the spectrum goes from. And as I mentioned in the last class, the lowest in energy are the radio waves. And the radio frequency tells us one thing about the chemistry whenever we bombard them with radio waves. That's what NMR does. So we can look at the nuclear spin on things that are visible within that are able to do the coupling, I should say, for the NMR spectra. The microwaves are for EPR spectroscopy, which we won't go into here. And in this class, we have IR, which we did in the last class, and of course UV vis. And the UV visible light, that's in the portion that will look at the excitation of electrons. And you've done that, you just didn't necessarily learn in Gen Chem perhaps what that indicated. But that's why it gives us the color. You did the colorimetric assays, or you may have done ELISA assays, which are colorimetric in the sense. And so that's because of the excitation in the UV vis spectrum. Okay, and of course X-rays are X-rays, and then we have gamma rays and cosmic rays, which would be the highest in energy. All right, so to review this part, we have to realize that energy states are quantized. What does that mean? If it's quantized, what's a quanta? What does it mean? Pardon? I can't hear you. Sorry.
Is it like orbitals? Having to do with kind of the orbitals and the positions of the protons and electrons?
Well, so protons wouldn't be in orbitals.
Okay, electrons.
Right? Yes, you're starting to get there. But just in general, quantum means you have there's a discrete packets or discrete steps, so to speak. It's not a continual, this continual spectrum for the energy. You go from one energy level to the next energy level to the next energy level. Okay. So there are these small discrete steps. So this is what the delta E equation comes from, in the fact that you can go from, take a photon of light, which has the energy, and if it equals the difference here, you can get the electron to jump from one energy level to the next energy level, or from 1 to 3 or something like that, from what you covered in Gen Chem. Now, for us here, we're not going to go to that level of detail. Okay, so what kind of energy states are we talking about? As I mentioned before, those that are in the radio frequency range, what that tells you, that equates to the energy that's found in the nuclear spin. Okay, so this is the lowest of the energy sources. Microwaves tells you about the rotation of it, which has to do with EPR. And then the infrared region tells you the vibrational frequencies. And we've already talked about how we're talking about the bending and the stretchings of the bonds. And then the UV vis actually tells you the electronic portion. So that really is talking about the electrons bumping from one energy level to the next energy level. And so you just focus your spectrophotometer, or each of these spectrophotometers focus on a specific range of wavelengths, and it can tell you different pieces of information about those that are spectroscopically not silent. Because we'll get to it in just a moment. Okay, so there are many different types of NMR. For us, the most commonly used will definitely by far be proton NMR. Then next comes carbon NMR, C13 NMR. But there are some other specialty ones, like N15. There's, let's see, N15 is the biggie. There's phosphorus, P32 NMR. Sorry, yeah, P33 NMR. But we're going to focus, I want you to know the most detail about the proton NMR, and then we're going to learn a little bit about the carbon 13 NMR. Why do you suppose that proton NMR is so important?
Is it because it's changing
I mean, the rationale is actually very, very simple.
so when you change the protons, you change the actual filament?
No, I mean, even more simple than that. Proton NMR is so important, or such a powerful tool, because that's the most abundant thing that we have. Like 99% of all hydrogens are protons. So you've got lots of it around, so use it. So plus it's, because you're going to find a deuteron, which is H2, it's silent. But tritium, which is H3, should be fine. However, it's in such a small amount that the likelihood of you having a tritium at every hydrogen location is going to be very, very slim. Okay, so it's the most prevalent form of hydrogen. Okay, so the nuclei that are most useful to organic chemists are going to be proton and C13. They both have this plus minus half a spin. As I mentioned, the proton is 99% naturally abundant. So you have 100 hydrogens around, 99 of them are going to be protons. C13 is only 1.1% natural abundance, which isn't all that large when you think about it. However, you have to realize that if you've got a mole of carbon-containing compounds, what's mole again? What? 6.022 times 10 to the 23rd, right? And so if 1 out of every 100 of those is going to be, C13, then that's still going to be a huge number. Okay, so that's why there's still enough carbon 13s around in that you're going to be able to see it. It's whenever you get below that threshold that it's going to become more and more difficult. Like if we looked at N15, that's the one for nitrogen. O17, some of those will be much more difficult because their abundance is much, much lower. Okay. And it's only raining now because I picked up my umbrella and I thought, no, it doesn't fit in my Mac bag. And I thought, I just won't. Of course, I knew the moment I set that down, it's going to rain. So, of course. Yeah, so Preston can blame me.
No, I brought mine.
Oh, okay. All right. Okay, let's get back here on topic though. So here, if we're in the radio frequency portion of this, that means that, normally we thought about spin, we were thinking about electrons. We would have, remember the quantum numbers, there's the primary, the secondary of this, where one of them tells you what energy level it's on, one of them tells you the shape of the orbital, and ultimately the one tells you the moment, whether it's plus 1/2 or minus 1/2, if the spin was up or spin was down. Well, that's electrons, but you have to realize the nucleus is also charged, and it's also rotating, okay? And so a nucleus can, in of itself, whenever it rotates around, it's going to generate this magnetic field, okay? So it's going around, there's a magnetic field, you can kind of think of it like the Earth. The Earth has a magnetic field because it's rotating around. So does, like, each individual nucleus, okay? And the magnetic field of one that's plus 1/2 is going to be the opposite direction of one that's in minus 1/2. And so since they're in the opposite direction, there's going to be a slight energy difference. It's just that normally, whenever you have like this beaker full of carbon-13 or protons around, they're all going to be averaged out because these are vectors. If you think back to physics, and it's really coming down now. And so if you think back to physics, these are vectors, and so the average, if you add all the vectors of, here's my Portico cup. It's just false advertising. It's not Portico coffee inside here, but we're going to imagine that it's full of protons, but they're just moving around, so all the vectors are going to be canceled out. So there's no overall magnetic, moment to this cup. All right. So what? Oh, this is just to show you that the distribution of all the nuclear spins is going to be random. And so all those vectors, it's kind of hard to tell. At least I had problems trying to see it, but I'll try to draw one on here. So for example, this is showing that one going up like that, whereas this one's going down, like so. But they're all going to average out because they're just floating around in the Portico cup, so to speak. At least today I didn't steal a sweet and low from Portico. Okay. Now, what if we take a big magnet, and, well, if you just think back to, I don't know, when you were a kid, and you had, like, magnets, and you would put them together, like, what would sometimes happen when you put two magnets together? They could repel, or if their poles were opposite, what would they do? They would attract, and so, but they're going to line up one way or the other, and so to speak. Well, if you put a really large external magnet next to this Portico cup of protons, then what's going to happen is they're going to line up. And so, the majority of them are going to be parallel to the external field. And I know some books use the capital H for the external magnet, some will use a capital B. I'm not a physicist, so I don't know why, but we just have the big arrow, that's the external magnet. But we can see where there's a slight majority of them that's going to be parallel to that, because they're going to want to get it in line, but there's going to be that few that want to go against the stream, okay? And so that this is trying to show you is that there's a slight majority that's going to be parallel to the external magnet, where there will be some that's going to be going against that magnetic field. Well, because of that, there's going to be a slight energy difference. Okay, those that are going with it, it's going to be a little bit lower in energy because they're going down that stream, so to speak, that magnetic stream. Whereas those that are going against it's going to be a little higher in energy. So this is what this is trying to depict. Was that someone knocking on the door? Just oh. Well, I was going to say, they've never knocked before. They just usually come on in, that kind of thing. So here, it's not the easiest to see, but the way that this diagram, that's not a divided sign. And so the way that this is trying to show is this point right here is the cup without the external magnet. So there's no magnet, and so we just have an equal mixture of both. But what happens is as we start to put in an external magnet, at this point right here, if we have a magnet that's this strong, we're going to have a slight difference. Those that are against the magnet will be at that energy level, and those that are along with it, they'll be at this energy level. Whereas as you increase the strength of that external magnet, you're going to increase the energy difference between the two. Okay, so at this point, if you have one that's at this strength, that's going to be the delta E. And then the stronger and stronger the magnet gets, the better the separation. I should say the better the resolution between the two energy levels. Okay. And so that's going to be directly proportional to the external magnetic field. That's whenever, if you start to look at NMRs, they'll talk about how many Tesla NMR, oh, we got a 300 Tesla or 800 or something, so on and so forth, in the sense that the larger the magnet is, the better the resolution is going to be. The one that we have, that we bought this last summer, it's really small. So because they run exorbitant prices. I mean, it's outrageous to get a new one or even get a refurbished one that's like a 200. It's just ridiculous. And so I just wanted to throw that out there because that's why some of your spectra, whenever we get a chance to run it later on, may not look like the stereotypical textbook spectra, just because the fact is that we have a weaker magnet. Okay. Oh, just some of the units, which should be a review. And actually, I've been using some of these terms already. But first of all, the Tesla, that has to do with the strength of the magnetic field. Whereas a hertz is the inverse second, the per second. And so that has to do with the frequency. And then, of course, energy is always in kilojoules per mole or kilocalories per mole. And just to let you know, a kilocalorie is equal to 1 food calorie. So that's why if you have your sweet tea that is, 150 calories, that's really 150,000. Just want to let you know that. Throw that out there for you, Preston. You're welcome. Kind of depressing. I used to, just a little side note, I used to have when I taught physical science, because I used to have to teach it like in summer school and things, or in the evening classes. And so a lot of them would bring like their junk food or their lunch or something with them. And I would say, okay, now we're going to figure out how many calories it is. And then just assuming, like obviously metabolic differences aside, let's assume how many times you have to go up and down Aventura steps in order to burn off your lunch or burn off that bag of chips. It's really depressing. So. Okay. Now, one other thing about this, trying to separate out the nuclei and the difference in the nuclei, is it depends upon the identity of the element that you're looking at, the nucleus. And so different elements and even different isotopes, like I mentioned the proton versus the tritium, they absorb the radiation differently. And so that means that they can have the same magnet and they will absorb it at a different frequency. So like your radio dial, you turn in to a certain frequency to pick up a certain radio station. You can do that with the NMR, so to speak. You turn it into a certain frequency. So what this is saying is you tune in, you have a strength of 4.7 Tesla for your magnetic field. If you tune in at 200 megahertz, you're going to see the protons. Whereas the carbons are at 50.4 megahertz. And so, because of this, you can't pick up two atoms at the exact same time. Or I shouldn't say two atoms, two types of nuclei at the exact same time. Okay, so you're not going to be running the proton and the C13 simultaneously, because it's like the old-fashioned radio dials, not the digital ones now, or the satellite one that you have now, where you can just program it in. Remember the old, well, you guys probably don't remember the old one, but I remember the old one in my first car. You had to just finesse it just right to pick up whatever radio station you wanted, because if you just got a little bit off one way or the other, then you've picked up, the Spanish station coming out of, El Paso. And so unless you're a big fan of hearing something that has no words, usually, because it's all static, but we won't go there. I digress. So, all right. But since they have different frequencies, you can't pick them up at the same time. Set your dial, so to speak, on whatever element that you're wanting to look at. Another thing is, and it's why it actually works really nicely with the that old-fashioned radio dial analogy, is that whatever environment that atom is in affects its frequency ever so slightly. And so if you've ever had the joy of having to use one of the little turn knob radios, then you know that you'll be driving, you'll be moving along, and you'll get in some type of environment and it gets kind of staticky, and so then if you just kind of coax it just right, you can pick it up again. And that's a similar thing here. And so because of this is why NMR is such a useful tool, is because a proton that's hanging off of a methyl group, for example, it's in one type of environment, but if it's a proton that's hanging off of a thiol, that's a different environment. So you'd have to finesse that just a little bit, ever so slightly, and you'd pick it up and you say, okay, that's a thiol, proton. And that's a proton that's stuck to an aldehyde or carboxylic acid versus an alcohol. And usually any nuclei that has either an odd mass number or an odd atomic number will have these magnetic properties. That's why I mentioned the fact that the deuteron, which is a 2, it's a H2, it's silent. It doesn't have the magnetic properties. However, the proteon, H1, and tritium, which is H3, they would. N15 does, but N14 doesn't. And so, things like that.
Does it have to do with their vectors, or why is it?
I mean, I'm not a physical chemist. Actually, I don't know. I just always accept that. That's one of my limitations. I accepted it. They told me, yes. All right. So now this comes to what's hugely, hugely important. There are two terms that get used around a lot, and that's shielding and chemical shift. Okay? All right, and so I do expect you to know what it means when we say something is shielded or de-shielded. It is not shielded versus a chemical shift. Okay, and there's downfield and upfield chemical shift, and this is where I sometimes use football analogies, and unfortunately, if you're not a football fan, I apologize, but I don't know how else to do it. American football analogies. So, all right. So, whenever you have this external magnet, it's going to affect the motions of the electrons as well. Okay, even though we're looking at the nucleus, it does cause, we got the nucleus, it's spinning one way, it's just spinning, and then we've got the electron orbitals and the clouds. We just can't see them because that's not, we don't pick that up on that frequency. But we know that they're there, okay? And it affects the way that the electrons move around, and those electrons help generate their own little magnetic moments. It's going to be the opposite direction of the external magnet, okay? For the electron, for the movement of the magnetic field that's caused due to the electron motions. So because of this, depending upon what atoms are making that bond or in that area, it can affect of how much of the external magnet that nucleus actually feels. So you can almost imagine that the more electron dense that's around, the little bit less of the external magnet is felt by the nucleus that's on the inside. Okay, so it's almost like a buffer, so to speak. So you're either going to have a stronger magnet in order to feel, for that nucleus to feel what it would felt if there were no electrons around it. And so the effect of the electrons and the apparent feeling, I don't know, the apparent, like what the nucleus on the inside feels, is called shielding. Okay, so the electrons are shielding the parent nucleus that's on the inside from that magnet. It's not going to shield it completely because the electrons are puny, but over the bigger scheme of things, but it affects it ever so slightly. And, oh, I didn't point it out, but RF stands for radio frequency. They just always use the term RF in NMR. So that's for radio frequency. That's the part of the spectrum for NMR. So the chemical shift is the measurement of how much shielding is occurring for that nucleus. Okay, so here we're talking, remember, they're showing, it's a little misleading in the sense that we see this carbon to hydrogen bond, but we're only at the frequency for the hydrogen. So we don't actually see the carbon, but that carbon's got electrons around it. And the electrons around that carbon is also affecting the electrons around the hydrogen. And however much electron density there is around this hydrogen affects how much of the external magnet that the nucleus feels for that hydrogen. Okay, so that's why if whatever the hydrogen is attached to can help it out with more electron density, then it's going to be more shielded than if it's attached to something that's going to pull the electron density away from it. So does that make sense? If it's pulling the electron density away from that hydrogen nucleus is going to feel more of the external magnet, more of the effect. And so it's de-shielded. Okay. And so it's this, whoops, didn't mean to do that. It's this measurement of the degree of shielding that causes what's called a chemical shift. Now, that being said, we have to have a reference point. Just like a numbered line would be useless to you unless you have a number that you're using as a reference point. There's 0, and then, you go 2 up or 2 down, but you have to have a reference point for something. And so the 0 that is used for both proton and C13 NMR is done by the compound TMS, which is tetramethylsilane. And so the reason being is what's the difference in electronegativity between carbon and hydrogen? Just as a review. They're about the same. Carbon is just slightly a little bit more electronegative, but it's about the same. Whereas silicon, is it going to be more or less? Like, does anyone know? We don't have a periodic table in here. But it's even less electronegative, right? Because it's below carbon on the periodic table. And so because of that, it's actually going to be giving some of its electron density away. And so that's why they consider the methyl groups in the tetramethylsilane like perfectly shielded, I guess, if you want to speak it that way. And so where it comes out on the spectrum, that's 0. That's the 0 point. And then things need to move downfield or upfield from that. I know we are, but the iPad is not any longer. So just a second. So we take this a break from our sponsors. All right, so this is tetramethylsilane. I don't expect you to know its structure, and I will call it TMS from here on out. But whenever I have you draw your own spectrum, I do expect you to put in at 0 the little peak for TMS for both carbon and the proton NMR. And the units that they use are called parts per million for the chemical shift, and they use this lowercase delta, which is kind of hard to see sometimes, but lowercase delta. Okay, because that means, just like the capital delta is a triangle, and that means, change, lowercase delta means just a little change. And there is a mathematical formula. It's kind of hokey. I mean, it should make sense. It's the position of whatever your signal is minus the 0 position. And so, of course, so anything minus 0 is going to be the original number. And then they just divide it by whatever frequency you've got your magnet set at. And then since these are such ridiculously tiny numbers, they multiply it by 1,000,000. And so that's the reason why it's called parts per million, ppm. because I have to multiply it in order to see, because we're talking very, very small differences here. Okay, this is where I get my football analogy. So, for whatever reason, both carbon and hydrogen NMR is not read left to right, it's read right to left. Okay, now the P33 NMR, it goes the opposite direction. Historically, I have no earthly idea why, but because of that, the zero is on the right-hand side for carbon and for hydrogen NMR, and all the positive numbers go to the left. Okay, so I apologize now, but that's just the way it is. And so they refer to anything further away from the zero going towards the left as being downfield, like you're going to go downfield to score the touchdown, versus if it's to the right, then it's called upfield. And so that's why 1 is upfield of 5, or you can think of 8 as being downfield of 3. So downfield means it's further to the left and a higher number. Upfield means it's a lower number and further to the right. And in theory, you could have negative numbers. It'd just be something that's even more shielded than TMS. And I can't think of anything off the top of my head on these NMRs that you would ever see like that. Some of the other types of NMR, whatever they use for the reference isn't always perfect at 0. Okay. And so this is just I will never give you a math problem like this, but this is how they figure it up. Of course, now a computer figures it up and spits it out for you. But what happens is, this is chloroform. Chloroform for proton NMR only has 1 hydrogen. And it appears at 1456 hertz downfield from TMS for a 200 megahertz magnet. So if it was at 800 megahertz, it would probably it'd be a better separation, because the bigger the magnet is, the better the resolution would be. But you just take 1456 minus 0, which is why I say it's kind of a stupid one, divide that by 200 megahertz, and then multiply that by a million, and you get 7.28. And so if you look at it on the actual spectrum, you will see a peak at 7.28 delta. And so that's what this is showing. And so we only have 1 hydrogen, so you just see 1 peak. And so this one doesn't show where the TMS would be at, but the TMS would be occurring right here. And so a lot of times when we draw it, and I have you draw yours, I'll just ask you to put in the 0. That way we know where 0's at. For the most part, if you notice the x-axis here goes from 0 to around 10 for proton NMR. For C13 NMR, it usually goes from like 0 to like 200. But it's at a different frequency. So that's why you don't have to worry about them interfering with each other. Okay. All right, so that's easily said and done if we only have 1 type of hydrogen. But what happens when you have multiple types of hydrogen and they're in lots of different environments? And so what kind of effects will that have on the spectrum? And like, how was that useful for NMR, or for determining the structure? So this hopefully would make sense. The more electronegative environment that hydrogen is in, the less shielding it has around it. So that's why if you look here at the fluorine is the most of the halogen. Well, actually this isn't looking at halogens. This is looking across the row 1 on the periodic table. So fluorine is more electronegative than oxygen, than nitrogen, than carbon. And of course then we have silicon. That's TMS, it's just being used as the 0. So if you see, just having another carbon nearby, it shifts it slightly to 0.9. Having nitrogen, which is slightly more electronegative, causes it to shift all the way down to 2.2, oxygen to 3.2, and then fluorine to 4.3. Okay? And so that's why I don't expect you to memorize these numbers. Do not memorize the numbers. I want you to understand the logic behind these. So let's draw our first There we go. You always have to put in the axes. I'll usually... Oh, I don't know how to do subscripts and superscripts on this. I'm going to have to write it out by hand, unfortunately. So you always should label it. So this will be proton NMR. And we're going to have, some baseline. And there's TMS, which is 0. And somewhere over here will be 10. But once again, you don't need to memorize the actual numbers, but just look at the relative locations. So we already know fluorine, if it's near the fluorine, it's going to be over here. Well, obviously it can't be attached directly to the fluorine unless it's hydrofluoric acid. So that general area would be where fluorine is. Do you think chlorine, which would be the next one, is chlorine going to cause it to go downfield, which would be shifting it to the left, or will it cause it to go upfield, which is shifting it to the right?
You see replacing a hydrogen with the chlorine?
No, if instead of fluorine, you have,
Oh, it would shift to the right.
it's going to shift it to the right. And so that's why we would just know for chloromethane, it's going to be somewhere slightly to the right. What about bromomethane? Where would the hydrogens be on that with respect to chlorine? It's going to be to the left or to the right? It's going to be upfield. It's going to be to the right. So then it would be bromine, or bromomethane. And then iodomethane would be even more. And so that's why you just need to know the relative, use the logic to get an idea. I'm not looking you to know the exact numbers like 4.3 versus 2.2. Don't do that, but just know like where the assignments are for where they would be shifting. Okay. Likewise, usually the number of bonds that it's making can affect it. So what I mean by that, and so if you guys were drawing this, you'd probably want to make a really big one, a really big spectrum where you can put things in. I can't, I'm really limited in my space. So I'm going to do some erasing here, so that way I don't have to constantly be drawing the exact same thing over and over again. But if I say that this was a hydrogen, that's hanging off of a carbon that's in a single bond, and I just put it there, what happens if it's a carbon-carbon double bond that has a hydrogen hanging off of it? Do you think it's going to be further upfield or downfield? Like, is a carbon-carbon double bond going to be more electron-rich, and so pulling more electrons away, or is it going to be electron, deficient, where it's going to say, okay, not take any electron, or not affecting the electrons as would be around the hydrogen? Is it going to be downfield or upfield from a carbon-carbon single bond? Pardon?
Would it be uphill because there's not as many free electrons to run around?
And so no, you have the right logic, but it's just the wrong word. It's going to be further downfield because of that. For that reason, I can't spit it out now. And so it's going to be, now the triple bonds a little bit, for that logic, triple bonds can be a little bit more wide-ranging. But whenever I ask you to draw a spectrum, and if you put the triple bonded one further downfield, then I would give you that, because that logic, if you look at the tables, it's a big ranging one because weird things can happen. But, so that's why for you guys, you could say, oh, there's the triple bond. It would be, whoops, that's supposed to be an H. It would be slightly further, downfield than the double bonded one. Once again, we're only looking at the hydrogens, but it's what the environment that the hydrogen is in, where it's going to show up. What if, here I'm just going to, now in this color, what if we have a hydrogen that's on an aldehyde, which once again, don't forget your functional group. So let's say that we have a hydrogen on an aldehyde, and now we're just going to talk in broad generalities. A hydrogen that's on a carboxylic acid. With respect to the bonds that we have so far,
Is the aldehyde gonna be the most shielded?
the most shielded or the most de-shielded? For the proton, remember we're talking about for the hydrogen. Will the hydrogen have more electron density around it, which is shielded, or will it have less because of the acyl carbonyl next door to it? It's going to have less. So if it's going to have less, will it be further downfield or will it be further upfield? Downfield. In fact, it's usually way down here somewhere. Okay, and the reason why is this is delta minus. That oxygen is very delta minus, very electronegative. It's pulling electron density. Not only is it a double bond, it's going to pull some electron density, but it's really pulling the electron density towards the oxygen. So that hydrogen is really exposed to feel the external magnet. Okay, more so than the TMS compared to the TMS. What about a carboxylic acid? Is it going to be pretty far downfield or is it going to be upfield? It's going to be pretty far downfield as well. Now, we're going to find out that it is a special case in some instances, in the sense that it's an acid. So what do acids do? They give up the proton. So a lot of times, there's sometimes that you may not even be able to, it may not be sticking around very well because it's already gone, so if you're at the wrong pH, it's already lost its proton, so you won't even see it because it's gone. And so that's why I say that it's kind of a special case. It's flopping off with the water and everything, because obviously you can't have like a pure, even glacial acetic acid is not 100% acetic acid. Okay. I'm going to have to definitely erase a little bit here. What if we have something like, maybe it's not going to let me erase. Yep. So I'm going to have to draw another one. Or I'll just put in a different color. What if we have something like a benzene ring? That's supposed to have 6 sides. And so we have a hydrogen hanging off a benzene ring. What do the electrons look like in a benzene ring?
Don't they kind of jump around a little bit?
Not just a little bit.
They share more.
Right, it's called delocalized. It's the one where it looks like a donut or a hamburger, especially if you're really hungry. To where if you look at the electron density, it's delocalized. And so it just looks like kind of like a little life preserver. Actually, it looks a lot like a life preserver, lifesaver. And so those electrons are just moving around. It's an aromatic compound. And so because of that, do you think that the way that those electrons are, that the proton or the hydrogen that's attached to it, is it going to be shielded or is it going to be de-shielded for the hydrogen nucleus? And so, because this is where you can kind of compare it to, not with the oxygens, but compare it to the stuff that we've seen down here.
It's more shielded, right?
No, it's going to be very de-shielded. Because the electrons are being pulled into the life preserver ring, so the protons that stick out are going to be less shielded. They're going to be more exposed. Okay, so the benzene ring, usually their hydrogens are going to be further downfield. Okay, and so just in general, it's going to be shifted far to the left. Okay. So that's why here's some of the actual numbers that we can see, like the sp2 hybridized and all that. That's a fancy way of saying double bonds. Okay, so sorry to burst the bubbles of many an organic chemist or textbook author out there. sp2 hybridizes means double bonds. So we can see the single bond, which is really close to the TMS. A double bond is a 5.3. And then this is the benzene ring that I was talking about, and see it's all the way down at 7.3. Once again, don't memorize the actual numbers, just the logic behind the fact that because of the delocalization here, it's pulling electron density almost like a little whirlpool away from the nucleus of the hydrogen that we got it set for. Okay, so at this point, I'm going to go ahead and stop for today, and I'll end class with prayer.